This lecture is on section 3.2 on Math 311, a course in linear algebra at Western Illinois University. The topic is matrix algebra. In particular, so last lecture we learned about various operations involving matrices, including matrix addition and scalar multiplication and matrix multiplication and transposes. And now we're just going to review a few properties involving these operations. And you're going to see that there's going to be some properties that look very familiar. They're very familiar to properties involving real numbers, but then there are also some major differences. So, and I'm just putting these, I'm labeling these theorems because that's how they appear in the book. So for this first one, theorem 3.2, if A, B, and C are matrices of the same size, that means the same number of rows and the same number of columns, and if C and D are scalars or real numbers, then we have the following. We have A plus B is going to be equal to B plus A. In other words, matrix addition is commutative. Then we have quantity A plus B plus C is equal to A plus the quantity of B plus C. A fancy way of saying this is that matrix operation, or matrix addition is associative. Number 3 says that A plus the all zero matrix is A, of course, and A plus minus A is 0, where we define minus A just to be the A with all the entries of A multiplied by -1. So -1 times A is the same as minus A. And that's actually how we can define matrix subtraction as well. I have a real number C times A plus B. That's just CA plus CB. And you have little c plus little d times A is little ca plus little dA. These two are kind of like a distributive law that involves matrix addition and scalar multiplication. And then we have number 7 says CDA equals CDA. This is kind of, I think it's called the associative law for scalar multiplication. And number 8, or the most apparent one, says that 1 times A is equal to A. Okay. And the proofs of these are very straightforward. And Math 311 really isn't a proofs course, so we're not going to spend a whole lot of time on proofs. But I wanted to say the way we prove that two matrices are the same is by showing that they're the same size and that all their corresponding entries are equal. That is, in particular, the ij entry of one side has to equal the ij entry of the other. So if we wanted to prove that A plus B is equal to B plus A, we would just look at an arbitrary ij entry. That is the entry in ith row j column. That's the ij entry. And the ij entry of A plus B is aij plus bij. And by regular community of addition of real numbers, this is bij plus aij, and that's the ij entry of B plus A. So from there we get A plus B is equal to B plus A. And all of these others are, basically can be done the same way. So there's nothing really surprising about this, except we have, we just use this notation for the all zero matrix. Okay, now things get a little more interesting when you bring matrix multiplication in. So if A, B, and C are matrices such that the expressions below make sense, that means that we're actually able to multiply these. So if we multiply, for example, B times C, we're assuming that the number of rows in B equal the number of columns of C. So rather than write down, all of that, we just say so that these expressions make sense. And if K is a scalar or a real number, then we have these properties. And again, this number 1 shows that matrix multiplication is associative. 2 and 3, these are distributive laws involving addition and multiplication. This is pretty kind of standard as well. It just says that because K is a real number, we can multiply K by AB, or K by A and then by B, or by B and then by A. and it doesn't. This is all the same thing. And then, as we alluded to last time, if A is an m by n matrix, the identity matrix of size n times A is equal to A, and A times the identity matrix of size m is equal to A. The only caveat here is that A does not necessarily have to be square. So m and n don't have to be equal. So the order does matter in this case. So we're talking I am here. That means the number of rows has to equal the number of columns here. So I think yes, that hopefully that makes sense. Okay, I got that right. Now, probably the most important one here is that A times B is not equal to B times A. We alluded to that before. Okay, that's the main difference. Matrix multiplication is not commutative. It is associative. That says what we have up here, but it's not commutative. And we saw quite a few examples in the last lecture. Before we start doing a proof, there's another little tidbits that might be very helpful when you're doing problems like this. Is that when if we let A be written in terms of its rows like this, so if we let this be the first row, A1 be the first row of A, and so on, and if we let B1 be the first column of B, and so on, then AB can be written as n columns, in which the ith column is just going to be A times the ith column of B. Okay, if you think about it, to forget the first column, you just be taking the first entry would be this row times this column. The next element in the column would be the second row with the first column, and so on. So it would really just be A times the first column of B, and so on. Similarly, we could also compute this as the first row of A times B, and the second row of A times B, and these would be the rows of AB. All right. So this isn't as helpful. This is a little more helpful than this. So this might be a good thing to keep this in mind, because it might be helpful later on. All right. So just to see a proof of these again can all be done by showing that the ij entry on one side is equal to the ij entry of the other. And in this case, we have that the ij entry of A times BC is equal to, well, what we say that this is A, and this would be BC. Okay, we do it this way from our discussion up here. And then, okay, well, remember that when you multiply these two matrices, you take the row over here and a column over here. So you take the ith column here and take the dot product of that with the jth column here. So that's what we get here. And so we have the dot product here. All right, now, this turns out to be equal to this. And this is not quite apparent, but we're going to, I think I'll assign this for extra credit. That we can prove that later on. So let's assume that if this step is correct, then this is AIB plus dot CJ, and this is going just to be the IJ entry of this matrix and this matrix. And then this is, we said this is AB and this is C. Okay, you are not going to have to reproduce this on a test. I know that's what you want to hear, but I just wanted to show you this is how the proof would be. And as for the extra credit, I'll reformat this and so it's in a slightly friendlier scenario. Okay. All right. Now going back to the matrix multiplication and how these how matrices don't commute. In general, matrices don't commute, but for each matrix, there will be some matrices that will commute with it. And we have a few examples here. And I'm going to start with example 2 because this is actually a little easier. So we have this matrix B, or this matrix A, and we want to find all matrices that commute with this. Okay, so we want to find all matrices B in the form of A, B, C, D, all 2 by 2 matrices that commute with this matrix here. Okay, so what are we talking about? What we want is the matrix 1, 0, 0, 0 times A, B, C, D to equal the matrix A, B, C, D times 1, 0, 0, 0. Okay. All right, if we multiply this out on each side, this is A plus 0, B plus 0, 0 plus 0, and 0 plus 0. Whereas over here, we have A plus 0, 0 plus 0, C plus 0, and 0 plus 0. Okay. And then if we equate all the corresponding entries, we get A equals A, which is not that surprising, but then we also get B equals 0, 0 equals C, and 0 equals 0. Okay. So B and C have to be 0. A equals A tells us that A can be anything, and there's no mention of D, so that kind of implies that D can be anything. And so what we're really talking about is the matrices, all matrices of this form, A, 0, 0, D, commutes with A. In other words, all diagonal, all 2 by 2 diagonal matrices. Commute with A. And in fact, it's going to turn out that all the diagonal matrices commute with just about any matrix, any square matrix, right? All right. So this example wasn't so bad. If we go up here to this first example here, we try to do the same thing with 3, -1, 1, 2. Okay, and if we do the same thing, what do we get? Over here we get 3A minus C, 3B minus D, A plus 2C, and B plus 2D on this side. And on the other side, if we multiply them in the other order, we get 3A plus B minus A plus 2B, 3C plus D, and minus C plus 2D. Okay? And so this implies that 3A minus C equals 3A plus B, 3B minus D equals minus 2A plus 2, minus A plus 2B. Then we have A plus 2C equals 3C plus D, and then B plus 2D is equal to minus C plus 2D. Okay, and we can see, I hope, that from this first equation, the 3A's cancel, and we get minus C equals B. And in fact, that's exact down here, the 2D's cancel, and we basically get the same thing, B equals minus C. And then so we can see that B, whatever C and B are, they have to be opposites of each other. And if we try to write everything in terms of, let's say, C, we'll get, let's say for this equation, we get A plus 2C equals 3C plus D. Okay, that's actually good because there's no B in here. And we can see that we can subtract 2C from both sides, and we'll get A equals C plus D. So turns out that A and B can be written in terms of C and D, and in fact we get C plus D is A and B is minus C. Here's C and D. Okay, you can play around with these others. We can see that this last equation is a little redundant, but you can see that any matrix in this form will commute with this particular matrix. All right, and in like advanced abstract algebra or advanced linear algebra, we're going to see that this is called the centralizer of a matrix, but don't worry about that. Okay, so every matrix has some matrices. Or at least every square matrix will have matrices that commute with it. Obviously, all diagonal matrices and some others as well. Okay, I think there might be one exercise in 3.2 that is kind of like this. Okay, so the last part about transposes of matrices. Remember, with transposes, a transpose of a matrix, you're just interchanging the rows and columns. So the transpose of an m by n matrix is in fact an n by m matrix. So the first row becomes the first column, and so on. The first once again, we're assuming that A and B are matrices, so that all these products make sense. And we see that the transpose of A is equal to A. That should make sense, because if you interchange the ith row and the ith column and then interchange it back, you get the original matrix. The scale, if k is a real number, basically because you can always factor out this k, it's going to be about the same. So Ka transpose is k times A transpose. It's kind of straightforward to check that the transpose of A plus B is the transpose of A plus the transpose of B. The one non-trivial or non-apparent statement says that the transpose of A times B is equal to the transpose of B times the transpose of A. Now let's see why that kind of makes sense. Because remember, if first of all, if A, let's say if A is m by L and B is L by N, all right, then A transpose is going to be L by M, and B transpose is going to be N by L. Okay, so we want here, that should make sense, because the number of rows here should be equal to the number of columns here. So that kind of makes sense. That's not exactly a proof of this, but let's just see why that is. So here's a proof of number 4. Okay. So if we want to show that this equals this, if we look at the ij entry of AB transpose, well, this is the same thing as the ji entry of AB, right? Where you just interchange the rows and the columns. Okay. And what is this? Well, this is the dot product of the jth row of A and the ith column of B. Okay, this is the dot product. Okay, because after all, this is a vector, this is a vector, and this is a vector. Okay, now the jth row of A is going to be the ith column or this will be the jth column of A transpose, and this is going to be the ith row of B transpose. And because we knew when we first learned about dot products, we can interchange the order of these. It doesn't matter. So this is the ith row of B transpose with the jth column of A transpose. But this is the ith row of one matrix times dot with the jth column of the other, so this is just the ij entry of the product. So this is the ij entry of B transpose A transpose. Okay. So that's why this is the proof of that. That's why it all works out. Okay, why it should be. So that's why matrix multiplication is a little funny. It takes a little getting used to. The number 5 is really just a specific case of number 4. When A and B are equal, when A and B are equal, you get A squared T equals AT squared, and then you can use little induction, multiply everything by on one side by A and so on. So that's not too hard to prove either. If A doesn't have to be, remember, a symmetric matrix is just a matrix which is equal to its own transpose, and in this case, if A is in any matrix, A times its transpose is going to be symmetric, and A transpose times A is going to be symmetric, even though these might be these will be square matrices, but they might be of different sizes. Okay. So why is that? So for 6, we have, if we wanted to take the transpose of A transpose, okay, this is going to be, okay, well, we take the transpose of this matrix, the transpose of AT times the transpose of A, but we know from number 1 this is just A. Okay. So the transpose of this, so that means that A transpose is symmetric. And similarly, if we do the same thing here, A transpose, this will be A transpose, transpose, which is A transpose A. So that tells us that A transpose A is symmetric. And then finally on number 7, if A is a square matrix, then A plus A transpose is symmetric. And the reason for that is we get A plus A transpose. We can basically use this matrix where B is replaced with A, and we get A transpose plus A transpose, which is A transpose plus A. Okay, which we can also write as just A plus A transpose. Okay, so the transpose of this matrix is equal to itself, so it has to be symmetric as well. Okay. All right, so there's a lot of properties, a lot of theory in this section. Not a whole lot of computations. That's why I didn't really, at least in this course, I didn't give you a lot of homework problems from that book. But you should definitely be aware of the properties of transpose and all the other operations. And thank you. I'll see you next time.